Welcome back. And today we are going to have the final session on GANs, and we'll be seeing how to implement GANs as well. Then we'll begin with we'll complete a set of models called autoregressive models, and in the next class we'll do some architectures like LSTMs and attention models and so on. So transformers and things like that. So that is the plan, and that would end at autoregressive models as well. And then finally, we'll do uh, recognition model, which is also a generative model, but it will be without the ability to generate new samples. We'll see these things, but before we get into all of those, we'll see we have almost come to the end of the course because we've seen GANs, we've seen VEs, diffusion models, flow models, energy-based models, GMMs and EM algorithm and things like that. But what we haven't seen is how to is an optimization for a metric. Is that what we'll be doing? We'll do Wasserstein GANs, and Wasserstein GANs will show that the Goodfellow GAN that we have or the JS GAN often see the JS GAN. There's a few problems. So first, let us. So I forgot to do one thing in the and that was for f of u was equal to, I showed you that T opt of P by Q or T opt of X, the optimal discriminator function for, so if you remember, if you recall, the F GAN objective, the loss of theta and W for F GAN, for any F GAN, I think I have done the homework for tail, reverse scale, and chi-square. But for F GAN, this was equal to the supremum over W, the expected value of TW of X, X being sampled from the data distribution minus the X being sampled from the noise, the generated distribution, F star of TW of X. And we have seen this conjugate function time and again. So this is the Fenkel's conjugate. And we have seen its property, the derivatives property, and so on. And this is infimum over all theta. And we showed that this ends up becoming this GAN where the generator tries to maximize or predict if it is belonging to a positive class, or that is the real samples or a fake samples. That is the discriminator tries to do that, and the generator tries to fool the discriminator if and only if for f of u, which was the Fenkel's function that we chose for the JS divergence for f GANs, was given by minus u plus 1 log of u plus 1 plus u log u. Right. And what we have to show is that T star T optimal of X is given by f dash px by qx, right? And then this is also equivalent to saying the conjugate's derivatives inverse of px by qx. We have shown this last class. This is shown last session. Right? For f being a convex function, convex and continuous derivative exists for f, if you assume. Okay, so let's take f dash u, and we get there was a u by 2 somewhere. Yeah, this is u by 2, and this would become minus 1 plus log of u plus 1 by 2 plus 1 plus log u. And this gets cancelled, and you end up having, okay, this was a negative sign, so this is this, and you end up having log of 2u by u plus 1. And therefore, the f dash of u is given by log of 2 times px by qx by px by qx plus 1, which is log 2 plus log of px by px plus qx, or q theta of x. Right. So this is what we were showing, and we showed that this is my T optimal of X. And this is clearly, we can see that for a fixed discriminator, again, in this method as well, in FGAN method as well, optimal T opt is at Px by Px plus Q theta of X. Right? This is what we see and we have observed. And you, as your homework, you can do F star the conjugate's derivatives inverse and show that this is exactly equal to this. Okay, so that's said and done. So we have shown the GANs objective, and the GANs objective is like, if you considering that we have this what do you say, the discriminator, the JS GAN or the Goodfellow GAN, and the JS GAN, the Goodfellow GAN, which is actually being implemented as a JS GAN, is a bit different, right? We remember saying that, see, this is, if you remember that the original GAN has this objective, right? It is a discriminator that predicts between the source and the real distribution, the fake distribution, and only this part of the loss depends on the generator. Therefore, the generator tries to maximize it. But in the case of the Goodfellow GAN, so this loss is equivalent to minimizing the JS divergence between the data distribution and the model distribution. This we have shown multiple times. But we say that the Goodfellow GAN says that, so this loss that I have, the star that I'm putting, the expected value of minus log of 1 minus d g of z, the z sampled from PZ distribution suffers from vanishing gradients. Vanishing gradients when discriminator is strong. And we have shown this multiple times in the previous session. And therefore, Goodfellow said that instead, optimize over z belongs to Pz minus log of d of gz. And now there you'll see in our code as well. And if you don't train the model, many times what happens if you do this Goodfellow GAN training, this is for the generator. This is for the generator that you do. This we try to minimize this loss. So the generator has this loss, and the discriminator still categorizes between the real and fake. So if I really draw this diagram over here, so this is the g theta. This gives me g theta of z. This is equal to x tilde from Pz. This is x. This is trying to predict, the discriminator is trying to predict real or fake. Real or fake. Yeah, the discriminator would have this loss. So this is my Goodfellow GAN. So once you're able to understand the algorithm, the math behind the algorithm, the implementation is very simple. It's often a neural network which with a particular objective function, which you have already been training in basic supervised models as well. So this is what this loss is, and the generator loss is G star is equal to the arg min of the expected value of z being Pz minus log d of Gz. Right, so this is over d, or this is over g. So these are the two losses that we train, but we will see that the literature says that the generator in Goodfellow GAN suffers from mode collapse. Suffers from mode collapse. And what is mode collapse? It means that, say, this is your px distribution. Say px distribution is something like this. Let us have multiple modes in the px distribution. This is my px. Often your p theta distribution could be something like this. So, for example, so this is a mathematical example, in terms of distributions. So in terms of distributions, you can think of it this way. But if you have, say, a MNIST data set, you could think, say, MNIST data set, mode collapse could be something like this. Collapse could be a model that generates, say, only 9 and 7 and ignores rest. This is mode collapse. And this is seen many times in literature and if you train your model multiple times, sometimes you'll see that mode collapse do happen. And this is why does it happen is what I'll show you now. So what is the objective of so remember, what is my objective? So my objective, my lemma is that what I'm trying to show is the gradient with respect to theta of d of expected value of z being sampled from pz log of d of gz, or say g theta of z, right? This is given by dkl, the gradient at dkl, and theta equal to some theta 0. We'll see at what theta 0 are we finding the gradients. The generated distribution and the data distribution minus the dj's divergence between the generated distribution and the data distribution. And this is very, very surprising. So this results in a very, very big problem. When we'll see the problem, we'll try to investigate the problem as well, but let's try and show this first. So this is my objective. This is my GAN objective, Goodfellow GAN. And this is in terms of a negative of a J's divergence, which we absolutely did not start from. We started from the positive of a J's divergence, and the gradients are exactly in the opposite direction if I do this loss. And let's see what is happening. So let us consider an optimal discriminator d star of x, right? Right, d star of x equal to px dg theta 0 of x, and you'll ask me what is p dg theta of x? The optimal discriminator for optimal generator g theta. Or you can take a fixed it may not be optimal, right? You could say that it could be for a fixed generator because you're fixing the generator and then updating the discriminator, and vice versa for a fixed generator g theta. It could be any g theta, right? It need not be one of the g theta. It could be any fixed value of the model of the generator. So for the fixed value of g theta, we know that the optimal discriminator is given by p by the Bayes ratio, right? So now what I'll do is the proof goes as follows. I will do some bookkeeping on the left. I will start from the DKL term between the model distribution and the data distribution. This is what I'll start from. Okay. Start from this. So I'll start from this term. And I'll show that this is, we know that this is PG theta, log of PG theta. I'm just writing the X term. So this is dx. And this is nothing but the expected value. Okay, I'll just, should we keep some space? We'll do that. So this is equal to the expected value of X being sampled from PG theta, log of PG theta by Px. Beautifully written. So now as soon as I do that, I can write this as the expected value of X being sampled from PG theta, log of PG theta by PG theta of 0 into PG theta 0 by Px. I just multiply and divide. So let us see which one will I take the Px with. Okay. PG theta. I'll just multiply and divide by this. So now, when I have this, right? So now I know an equation from this. This is given to me. PG theta in terms of PG 0 is given to me. So therefore, if I write this, if I take this ratio, I can write it in terms of the discriminator, right? So like we did for the ratio GAN. So this is why we did it then. So therefore, my DKL term. So I'll just maybe zoom this in. Just yeah. So therefore, my DKL of PG theta Px is equal to the expected value of log of PG theta 0 Px by Px, X being sampled from PG theta, right? Plus you have the expected value of X being sampled from PG theta, and you have PG log of PG theta by PG 0. Right? So this is what I have. And as soon as I have this term over here, I can write this as the expected value of X in PG theta log of the discriminator star of X by 1 minus discriminator star of X. A negative of this, right? So you can see this equation from dagger. I'm just taking dividendo. So it's d star by d by 1 minus d star is equal to Px by Pg theta. So if I have to invert it, I get a negative of the log. Okay. So I get this and I have a KL divergence term between Pg theta and Pg 0. Okay. Now you see, as soon as I do this, things are going to be sorted. This is because I will get, this is what I wanted, right? This is what I wanted. The log of the discriminator, right? Somehow I wanted this. So I could write this as X being Pg0, Pg theta, log of, or I could just say Z from Pz. I'll just Z from Pz is the same. The generator is going to generate the data, the d star of g theta of Z plus expected value of X being sampled from Pg theta log of 1 minus d star of X. And again, when you see this, plus the DKL of PG theta, PG 0, theta 0. Okay. So now when I see this, I will take a gradient on both sides. I'll take gradients with respect to theta on both sides. Taking gradients on both sides. So this is my dKl. This is dKl, pg theta, px. The gradient with respect to theta. I'll take the gradient with respect to theta. This is a function of z, so I can take the theta derivative inside, and theta at theta 0. I'll do this. I'll take the theta at the theta 0 for which the d star is defined. So theta is at, I'll compute it as theta equal to theta 0. Theta equal to theta 0. Take the derivative and put the value at theta equal to theta 0. And this is the derivative and theta equal to theta 0. So now as the last term that you see over here, this is 0. Why? See, dKl is minimized at pg theta equal to pg 0, theta 0, right? So now if I take the derivative, therefore the derivative value at theta equal to theta 0 has to be equal to 0. So we know that extrema points have derivative equal to 0. Therefore, this term just can go to 0. We have already written this, okay? This term here is nothing but the J's divergence, right? For the GAN, for a fixed discriminator, this is the dKl, dJs between the model distribution and the data distribution, right? Or whatever direction you want to write. The J's divergence is symmetric. Right, so this is nothing but the px dg theta for any theta, right? So this is exactly the loss that we have shown here. This is my J's divergence loss for the generator, and that which have shown multiple times in the session 7 and 8 that this is equal to the J's divergence, both in terms of FGAN and also by optimizing the optimal discriminator. So I've shown that it is equal to the optimizing the J's divergence. So therefore, this equation becomes, this becomes the gradient of, or we can write this, the negative of, which is the Goodfellow GAN log of d star of g of z theta equal to theta 0. This is nothing but equal to, so I'm taking this on this side. So I'm getting gradient of dKl pg theta and px minus dJs between px and pg theta, right, at theta equal to theta 0. Now you see this is a very, very big problem. The generators, this is my generator's loss. This is my generator's objective. This is my gradient of the generator. So now the gradient of the generator has two parts. So the gradient of the generator, as we have seen, has these two parts now. We showed just now, has this part and this part, right? Let's try and interpret this. Let's copy this equation for fresh. There's a negative sign there. Please be careful. So this is the negative sign. So now, really don't need to put this here, but okay, I'll just put it. Just derived it just now. So whatever the Goodfellow objective was, which is this is the objective, the GAN objective for generator. It's the GAN objective for the generator, which can be written as a reverse scale divergence. Reverse scale, and you have a opposite of Jensen-Shannon. This solves a lot of understanding problems in the GAN paper. So we know that reverse scale, if my p theta px is defined by this way, dKl is the reverse scale, This is defined by the expected value of x being sampled from p theta, log of p theta by px, right? So now we can clearly see something like this happens. This is my p theta, and this is my px. Then at this point, p theta by px is very low, is low, and no penalty is incurred. So therefore, mode collapse is bound to happen. Collapse is can happen as model is not forced to cover all support of px, right? So this is the problem with the reverse KL, which is there in the Goodfellow implementation. Similarly, this is my one problem, and the second problem is opposite of the JS divergence. Gradient is opposite of JS divergence, which is going to be harmful, which is harmful for the model. Because ideally I want JS to decrease and Goodfellow increases it. But the problem is, like, the thing is, shown works okay-ish for empirical problems. It works good actually. So works good for empirically. So people go on with it. So multiple times if you train and works good empirically, people go on with it. But sometimes this mode collapse problem has to be solved somehow. So we have been able to show you the mode collapse problem, sign opposite sign of JS divergence and reverse KL. So now what I'll do is I'll give you an alternative to GANs. The GANs which uses matrix like KL divergence, DKL divergence, reverse KL, JS divergence. Instead, what we will say is we will define a metric or another distance measure, which is called the Wasserstein distance, which is a continuous sort of a distance. It is not going to be a constant function for a p theta. It is a constant. It is slowly going to change with changing theta, and this will have proper derivatives with respect to theta and things like that. So what we want is we want a gradual mapping from theta to p theta. In the original map, a continuous map, a gradual map from theta to p theta. So normally what we're doing, we were learning a generator G, which was taking a value on Z and directly mapping it to the p theta distribution. But what I'm trying to say is for this model that I have over here, I want a metric that makes the mapping between p theta and theta continuous. So we'll try to understand what does that mean. We'll try to see what Wasserstein distances are. But yeah, so this is the overall idea. And well, I'll just put some space, should I? The alternate approach or a new divergence measure that we have, we want it to change gradually on changing theta, and we would define this as dw of p theta and px, and we want them to be symmetric again and things like that. So Wasserstein distance is one of the measures to do that. Unlike F divergence, which becomes a constant and sometimes can become at optimality, it goes to log 2 and things like that, and becomes maximizes out, the gradient becomes 0 and so on. This will never be like that. So this is an optimization problem. It defines a transport function between P of theta and P of R. So let's try to understand what does it mean. So copy this. So I think I can start from here. There's some space. We'll start the derivations from here so that we're able to understand clearly. So this is Wasserstein's GAN. And what does Wasserstein GAN? You can look at the notes that I have, but I'll try and rewrite the thing or rederive the thing. It says that you have two distributions, right? All this while Px and P theta, we were telling that we define the distance between these two distributions as dKl between Px and P theta. And it was like Px log of Px by P theta. And we said that this is, and we are saying that this is a constant function that I have, which is a function of theta as well, but this is defined. This is not an optimization problem. This is a deterministic function that I have to determine the matrix. On the other hand, and it will max out. It will max or minimize out. It will minimize as Px goes to P theta. And we want that, but we also want, and the sometimes the KL divergence loss is not continuous, is not very smooth. And we have seen that we have the problem of Goodfellow GAN. It is, your derivatives do exist, but in the Goodfellow GAN, we had this problem that we have the reverse KL, which is going to max out at some, if you go to one mode and things like that. And instead, the Wasserstein GAN says that, okay, I will do a F divergence measure, but this will be a new way to understand this data. So I will try to understand two distributions by try to see the amount of work that I need to do to convert one distance to the other. So this defines, the Wasserstein GAN defines a new metric. So see, we have to give motivation in some way, but the motivation for using this new metric is sometimes written in literature to be that this encourages models to learn better compared to KL divergence, reverse KL, or the JS divergence, because this is an optimization problem which does not always max out to a value, or it does not always become a constant. So a new metric that is defined as the amount of work done to convert one distribution to the other. So this is also called the earth mover's distance. So it's like I have this bin structure. You can understand the binning structure over here. So you can see that the first bin that I have is tall, is short, and here it is tall. The bin 1 that I have is tall, it's tall, here it is short. So whereas bin 2 here is very short, where it is tall. So now to make the bin 1 taller in Px, what I can do in P theta, so I can put some mass from this bin 2 into bin 1. I can put some mass, right? Similarly, I can put some mass. So again, you can see bin 4 here is tall, where it is short in the other Px distribution. So I can put some mass here, and slowly this will end up looking like Px. Right? So this is like the amount of from each of the bin. It's like you can think of it from each bin, I will move some mass such that the final distribution becomes like Px. This is all you need to take away from Wasserstein GANs. So what am I doing? I'm trying to move some percentage of mass from all bins. So it's like, if you see, it is the, so if you see this, if I draw down this distribution, it's a joint distribution. So if I have X and this is my Y, right? So say this is my X. Let's say that this is P theta of X, and this is my Px of X, and this is my Py of Y, right? So if I have two distributions, X and Y, so say I number the bins here. So this is called a transport plan. Transport plan. So 1, 2, 3, 5, 6. Yeah. So this is my transport plan. Transport plan is defined as a joint distribution. So now you can think of it that I'm transporting mass from X to Y. So X had this. So X has X equal to 1, X equal to 2, and all the way X equal to K, Y equal to 1, dot, 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 Y equal to K. So X equal to 1 has this mass, amount of mass that I have, right? Say I have this amount of mass. This is X equal to 1. So now some percentage of that mass I will be moving to, say, Y equal to 1. Say I'm putting some percentage of mass on Y equal to 1. Some percentage of mass. This is M11. This is say M12, M13, all the way to M1K. So this is, I'm saying, from this bin, I'm going to redistribute it to all the bins, right? So from X, I'm going to redistribute to all of the values in Y, right? So Y could have something, but it's a transport plan. It is going to tell me else what percentage of mass in X1 is going to YK, right? So this is like for every bin that I have, X1, X2, X3, X4, and so on till XK, I'm going to move some percentage of that mass all the way to the bin K or I to K. So one thing you can see that this summation of, say, they say this transport plan is defined by P of X comma Y to 0 comma 1, because the probability at the end of the day, mass is normalized mass over here. So if I do mu of X equal to 1 and Y equal to Y from 1 to K, this you can clearly say that this has to be the probability of X equal to 1. Because there has to be the marginal, because this is the total mass that X1 has, right? So whatever mass X1 had, I'm redistributing it. So if I sum over all the masses that were redistributed, it should be equal to the mass that X1 had. That is the idea. So it can be written as the integral of dxy dy is equal to the px distribution, the data distribution, or whatever distribution you're trying to tell. If you're marginalizing over, so this is a constraint 1. Constraint 1. Similarly, your y's would have a distribution, right? So your y's, on the other hand, say would have a distribution. Say y equal to 1 was tall, and to convert it to x, there would be a plan to say distribute here, 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 and so on. So right, similarly, so this is distribution from y to x. So they are all the same. You try to distribute from x to y or y to x. The measure that I'm going to get on both sides is going to be the same. This is because if you sum over, similarly, if I sum over p of y equal to 1, x is equal to k, k equal to 1 to capital K. And this I should get. What should I get? If I see now I have, so these terms that I have over here, these are the terms that is distributing the mass in y equal to 1, whatever mass was there in the y's distribution in the first bin, and I have distributed it to the x's bin. And now if I sum over all the x's bins, I should get whatever mass was there in y's bin. So therefore, this is going to be equal to the p theta of y. So this is what we are saying. So this is constraint 2. Or in other words, now mu of x comma y dx over x should be equal to py of y. So these are the two constraints that we have. If you have to convert, you have to see what is the amount of mass that you're converting from one to the other. So the work done under a transport plan, under a transport plan nu of xy, right? So you're trying to do some work. What would be the work done? So the distance that you're moving from x to y, say x is some bin equal to 1, and this is bin equal to 3. So therefore, there'll be a distance between these two bins. So it could be multidimensional and things like that. So this is my distance. So therefore, work done is proportional to distance into mass. So I'm not taking gravity into account here. Normally, people will take gravity into account to make it the mass into force. So the masses, these are all normalized masses between 0 and 1, and gravity has been normalized. So this is going to be proportional to this. So whatever work is done to transfer work done between x and y to convert between x and y is just proportional to this. So therefore, the total work that I have, the work done total work done that I have, this is going to be the summation of all x comma y mu of xy x minus y. So there could be repetitions, but they will be symmetric repetitions, and then they really won't matter. At the end of the day, what I want is x to be looking exactly like y, and that's the goal. And this transport plan will tell me how it should look like. So therefore, if you do the diagonal of this, if you see the diagonal of this matrix for a perfect transport plan, when the two distributions will be merging to one another, this will just be the diagonal matrix. You don't have to shift anything, right? So you just have the diagonal matrix and you will have nothing else for. So you will have only this. If px equal to py. So you, whatever is in px, you don't have to do anything. You just keep that in px. You do whatever was in py, you just keep it in py. And the rest of it was you didn't move anything, right? So therefore the loss again becomes 0. So the idea is x equal to y. Therefore the distance x minus y equal to 0. And nu was equal to nu xy is equal to 1. So therefore rest is, so therefore this product is again equal to 0. And rest of it is 0 as well. So therefore d w px py minimum is equal to 0. This is what we are showing. This is the minimum Wasserstein distance. And that is quite evident. Right, so clearly this is the total sum, and then if you can do that, this is nothing. If you in continuous space, this is going to be mu of xy, x minus y, dx dy, which is nothing but the expected value of over nu's distribution of x minus y. Right, so this is some p norm that you will have. So the Wasserstein distance, so the w dw, this is the total work done for the transport plan mu, the dw of, so there could be multiple transport plans, like infinite of them. So in one of them, I could move move my mass from these bins to this bin, which is going to be a lot of work, much more work because it's farther away. In some transport plan, I'll be closer by. So the closest and the minimum work done that I have to do is need to find as the minimum work done across all transport plans is the W distance, Wasserstein distance, right? So between Px and P theta, if I have to define this, so this is going to be the expected value of the infimum over nu in, say, I define all transport plan between Px and P theta. This is all possible transport plans, possible joint distributions, so that integral of px or so that integral of nu x y dx is equal to px, and integral of nu x y dy is equal to py. These are the two constraints, and I can have any joint distribution on the earth with these two constraints, and I will check all those joint distributions. I'll check whichever is the minimum, has the minimum work done, and that is defined as my dwp or sometimes in papers it's written as dwp of px comma p theta as infimum of nu belongs to pi, px and p theta, x minus y. So you would, so this is often used as a metric, right? We will come to DC Wasserstein GANs, but before that, we will see that this is often, I'll give you as an assignment, often used as a metric to see how close two distributions are in generated space, to see how close two distributions are, right? So for example, how good is the GAN generating? Is a GAN or a diffusion model generating? So in this case, what you will do is you will have a set of generated data, You will have a set of real data. You will pass them through a inception network. This is a convolutional neural network. You could pass it through any convolutional network used for feature extraction. Inception net. Could be any layer. You could take it features from a layer. So you get features x theta and you have x real. And what you will do is they will have some distribution. P of x theta and P of x real will have distribution, and you will find out the W2 distance between them. And this is called the FID, the Frechette's inception distance. You'll see this in a lot of generative literature and generative learning AI literature, Frechette's inception distance. Okay, so this is called the Frechette's inception distance, where you see the distributions of the features, the high level features in both the generated data and the real data. If this is small, if you don't require to make much transport between them, which means that you would be very similar to one another, and therefore they are very close to one another. That the generated data is very similar. This is how you see how you two data distributions are similar. So now we have understood what is Frechette's inception distance. We have understood what is the Earth's mover distance, and we have defined it as an infimum of minimum over all possible transport plans. So if it is important to remember that the integral of nu of xy dx has to be equal to px, and the integral of nu y xy dy has to be, this is marginalizing over x, so this is going to be y and this is going to be x. Right, this too has to be maintained, and you could have any joint distribution in the world and you can optimize over it. And you have seen Frechette's distance as well, and you can look at the example that I gave over here, the percentage of the mass that I'm moving, the percentage of the mass that I'm moving, y equal to 1, this is x equal to 1. So this is exactly what I wrote down over here. So you can clearly see that this matrix that I have defined is defined as an optimization problem. Matrix is an optimization problem. Optimization problem, and not a fixed value like, or fixed function like KL or JS, which often has convex or asymptotic behavior at the end. So that is fine. So now in Wasserstein GANs, what I'll do is I will try to first, what I'll do is I will have this generator, which will minimize the distance argmin over theta, say W2 of Px and P theta. So yeah, so once I do that, so I can write this as the loss function as L of theta as minimum over theta and minimum over. So this is how we have defined the infimum over all possible transport functions, right? Minimum over nu in pi of px p theta, the expected value of x minus y pth norm, right? This is how I will be defining this as over the news distribution, when nu of x comma y is what you're going to get, right? So now you will ask me, okay, sure, but there's a big problem. But how do I optimize over all distributions? All distributions of phi of px comma p theta. And this is where the Rubinstein Kantorowicz duality comes in, which is beyond the scope of the syllabus. This is beyond scope. So it is shown that the minimum over nu of a joint distribution, for if you have to minimize over this joint distribution over x minus y, this is given by the supremum of over w, the expected value of x from px, if w of x minus expected value of x from p theta, if w of x dash, right? So this is what it is defined as, right? So this is, if you do this, you can derive that this is an optimization problem. So the minimum, trying to find the minimum distance, is trying to have this function f w, which outputs a real number, which takes in x and outputs a real number. And what I'm trying to do is I'm trying to see the expected value of that real number for the real distribution and the fake distribution. So you can see, if you see this is exactly equal to energy-based model, right? This is an energy-based models equation. So you are seeing the difference in the energies for the given distribution. This is exactly like a EBM objective. Objective for a fixed theta generator. So now what will I have? What will be my structure of the, so there is some properties that you must have remembering, must not forget remembering, is that this function fw should be a Lipschitz 1 function. It should be Lipschitz smooth. That is, it should have gradients bounded by 1. So what you do is you say that f of x1 minus f of x2 by x1 minus x2 must be less than 1. This is what this function must be. This is a condition that has to be enforced. Only in these functions can you super maximize over this set. And then in this Wasserstein GAN, you can think of it in 1D. What is Lipschitz smooth? Lipschitz smooth, which means that if it is a 1D case, so f of x1 minus f of x2 by x1 minus x2, limit x1 tends to x2 plus, is bounded by 1, so which means that f1 x dash should be bounded by this. So if it could be a more absolute value, should be this is generally the absolute value for 1D, which means the gradients have to be small. Gradients have to be bounded. And therefore, if the gradients have to be bounded, how do we implement it in real life? We'll see that, but let's write down the entire equation first. So now I know that my Wasserstein GANs, the distance between the data and the model distribution, is given by supremum of fw being Lipschitz smooth, expected value of fw of x from px minus the expected value of x from p theta, fw of x. So now this is just the distance. Therefore, theta star w star is equal to the infimum of over theta. That is, you're trying to also minimize the distance. You'll have to minimize this as well. Minimize the distance. So minimize this infimum over theta of W of Px comma P theta. This is basically equal to infimum of supremum of, again, you're getting the GAN formulation. This is exactly the GAN formulation that you have, or the FGAN formulation that you have, but the output of the function is now a real number. This is all that the Wasserstein GAN is going to do. So you can see that this model is going to give you very, very good numbers. And as it is, you're seeing that the likelihood also in wormholes can be interpreted as an EBM. You can directly compute likelihoods from it and so on. Okay, so now what is the architecture? So this will be taking FW of G theta of Z, right? Where Z is being sampled from Z. Same thing, right? So I will take let's say a normal 0, 1 distribution. I will get data sampled from P theta. I will get the real data. I will get a real number corresponding to real or fake, and I'll take the difference of these two. And when I take the difference of these two, and I will then optimize for theta. And see here, there is no problem of vanishing gradients because that is not going to max out. The Wasserstein distance doesn't have those properties, and it is going to be implemented exactly like being like a GAN, where this discriminator or the critic network is just going to give me an output of a real number, right? This is going to give me a real number as output. Okay, this is the idea. Okay, what I'll do is I'll go to the coding at the end. I'll finish up autoregressive models as well, and then we'll see the implementation of GANs. But as I told you, this has to be Lipschitz spontaneous, or the gradients have to be bounded. And to bound the gradient, the paper puts again clips the gradient between -1 and 1, or puts a gradient penalty, or regularizes over the weights. So what you can do is you can take the gradients of with respect to theta of the loss and put a regularizer. You could put a penalty on that. This is a regularization penalty. So regularizing weights or gradients, not exactly weights, but gradients. This is the. So what you do is you take the gradient of the data and take the absolute value and say that this has to be very, very small. That's what we want, right? So this has to be bounded gradients, regularizing gradients or bounded gradients. Okay. Very nice. So now we have learned Wasserstein GANs. Wasserstein GANs is a GAN which uses earth movers distance, which converts one distribution to the other. And what happens here in these Wasserstein GANs is you use a critic network, which is going to take the values of the real data and the generated data and give you a real number. And the difference between the real numbers of the real and the generated data is going to give you the optimization. And it's often, and you can see it's the difference between two distributions value, which is very similar to the energy-based model. So if you remember the energy-based model, you had h theta here and h theta of x here, and x was being sampled from the p theta distribution, right? Or q theta distribution, whatever distribution you were using there. Okay. So this is my WGANs, and we have come to an end of all GAN models. What I'll do now is I'll go to autoregressive models. So just to see similarities, I'll just write it down over here in case you haven't seen. Similarity between WGANs and EBMs. Right? So this is my WGAN objective. Theta star W star is equal to infimum over theta supremum over W, or f of W less than 1, the expected value of FW of x being sampled from Px minus the expected value of Z being sampled from PZ if W of the generator theta of Z, right? So now this is or this is equal to saying the expected value of X being sampled from the theta distribution if theta or if W of X. Right. So now this is WGAN, Wasserstein GAN. And if you see the energy-based model, EBM, such that log of P theta of X is e to or minus H theta of X minus log of the partition function. If you see the log P theta of X, and you had done this optimization in the previous session. If you go to energy-based models and you remember this, so where is the objective function? The gradient that I used to take. So you could see that the gradient that I have over here was computed sorry. So the gradient that I was computing the gradient with respect to log of P theta of X was equal to the expected value of the gradient of H theta of X, X being sampled from Px, minus the gradient of, so you could just take the gradient out completely outside, X belongs to the P theta distribution of H theta of X. This is exactly what we got in the energy-based models, if you can remember. Right? What was the thing? There you go. So this is what we were minimizing, right? So if you see the signs, there will be very, very similar signs is what I'm trying to say. So yeah, somewhere. Here you go. This is what we are maximizing. So the equation that I wrote is now a minimizing equation. So you can see the log P theta, the objective function, the theta star is the arg min over theta of the expected value of H theta of X minus X from P theta H theta of X, which is exactly formulation of the energy-based or the Wasserstein GAN. See? Right? So this is exactly what we were seeing, and so we're very happy to see that this is actually what you're doing is you're learning an energy model within the Wasserstein GANs. Okay, this is another interpretation of the Wasserstein GANs. So here I'll just draw the DC GAN that I've implemented, but before that we'll go into autoregressive models. And we'll try and understand. This is very simple. It will take me only 15-20 minutes to explain to you what are autoregressive models. So think of it this way. Say that you have so I'm changing gears, all this while we were dealing with images and any data that was that had spatial correlations and things like that. And we didn't take a special structure of the data. But in autoregressive models, there's a special structure in the data. There is a special structure. And we will be dealing with these special structures. These are sequence to sequence models and language models and things like that, and EEGs and things like that. All of these, which are time series data. These are time series data. Right. So this is something to learn from. So what can we do to get time series is what the question is all about. So the idea is, say, for example, I am writing this sentence. Say I have this sentence. I am going to, so this, what its model is going to do is, it is trying to predict what my next word is. So we'll take sentences for ease of understanding, but this could apply for any feature. So these are, this I, as you know, would have some features. These would have some features, and this can be glow features or things like that. So these are NLP tokens, NLP features. So natural language processing features that you're using, we'll see how we are learning them, but you can think of them as vectors. Each word is mapped to a feature vector in k-dimensional space. That's what it is done. So what we do is, we're trying to predict the next word. We'll say, what is the probability of x5 given x1 to x4? This is all what an autoregressive model is. This is all it is. So what does it mean? So I'm going to say that xt given all x from 0 to capital T without T is only dependent on xt 0 to T minus 1. Right? It's like predicting the next token based on all the previous tokens. So it's like I could say that x5 could be a school. School could be a word that the model will predict. Right? So this is one of the ways to maximize the probability. So first thing I'll do is, this is what our language models do, and language models could, so language models are sampled in this way. So if you have a model that takes in history x of I, so say f being the model which takes x of x less than I and converts it into xi, which means that all the tokens in the past predicts the present. Example is sentence completion. Okay, so you complete a sentence. The next word depends on the rest of the previous words, is the idea. So if you have to sample, so say write a new sentence. What will you do? How will I write a new sentence, or how does all your chat GPT and things like write new sentences? They do this. So they say x0 is some dummy word. Say you are going to say it's a dummy word. Say I could say I or a space, or you could randomly sample any word, randomly sample a word. Sample from the PX distribution, say, or the data distribution directly. So this is like marginal frequency of every word, marginal distribution of every word. So for example, the would be there multiple times. So maybe the sentence starts with the. Most of the times the sentence starts with the. That's fine. And then what will I do is x1 would be sampled from p theta of x1 given x0. Once I get x1, I'll sample x2 from p theta of x2 given x1 comma x0. x3 from p theta of x3 given x1, x2, x0. Right, so this is what am I going to do? I'm going to take x0, predict x1, take both of these two, predict x2, will predict all of these and predict x3, and this will continue unless I create I output. So dot 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 unless xt is equal to the null sentence. So null token, where stop token. It's used as a token in that field where we stop a sentence. So let's see how we will learn this model. The joint distribution of the data. Why can I do this? Why can I do this? You can see that given the past, the idea is given the past, the current, the current output is independent of everything else. So let's try and do that. So we will do this. Px1 to t, let be a t length sequence. So what will I do? I'll say that I'll put xt given xt minus 1 to 0 into probability of xt minus 1. This is joint probability or just law of conditional probability. As soon as I do this, I can write p of xt less than xt. Right. So whenever I'm writing less than xt, this includes x0, x1, wherever you're starting from, x2 or xi minus 1. So similarly, I can write xt minus 1 less than t minus 1 dot x of 1 given x0. So this is nothing but the product of, I can product this out as the product of I equal to 1 to capital T, p of xi given xi minus 1. Right? So this is this is called the autoregressive model. This is all to an autoregressive model. The joint distribution is given by a product of the independent predictions of each token given each of this past. This is the joint of the autoregressive model. Okay. So now let us take one example for real numbers. Even if it is not real number, you can project and use a neural network and project it to a real number. Say we assume stationarity here. Say we have a curve like this. This is my time and this is my xt. So if I have to predict, so this is EEG. And I have to predict the EEG at this point. EEGs are recorded from the brain. If you remember, if you know what EEGs are, they are like ECGs, but of the electrical signals of the brain that tell you if what activity you are having in the brain, if you have some epilepsy or things like that. So I will be using this window and I will be predicting this, everything till t minus 1. Right? So now it could be used for stock prices, EEG, sentences, and any sequence or any time series. So what will I do? I'll say that this EEG says stationary. That is, if I start from T0 or capital T0 and model up to T0 or TP, this is the same as modeling from TI to TI plus P. So this, irrespective of where you start from, the joint distribution remains the same. This is what I'm going to write. So 1 to P is the same as T plus 1 to T plus P. So if you take a chunk of P values, a sliding chunk of the distribution of sliding chunk of P values is stationary, is same. It's called stationarity. Okay. So what I'm going to do is I'm going to say that xi, I'm going to model this as, I'll do two things over here. I will model this as, number one, I'll say probability of xi given everything else is going to be the probability of xi given xi minus p to xi minus 1. So what I'll say is I may have a long length sequence. So this is 1, 2, dot, p. This is my xi. I may have all this in the past, but my window only will consider predictions from this. And it is independent of the past, independent here. Independent less than p. Less than p equal to I minus p. Okay. Okay. So now I'll say that since it's let us assume that it's going to predict xi's. So what I'll do is I'll say that xi given xi minus 1 or This distribution will be modeled by a normal distribution of xi, which is a real number, summation of alpha I equal to 1 to p x or alpha j x of I minus j and some constant. If I do this, the loss would be the loss at time t. You can see this is going to be a cross entropy loss, MSE loss. So you will get alpha 1 star, alpha 2 stars as a normal distribution if you assume. So this is an MSE loss. Alpha p star is the argmin over all alphas xi minus summation of I equal to 1 to p alpha j xi minus j squared. Right, this is all this model is going to do. This is called the ARMA model or autoregressive moving average. So what you're doing is you're predicting the next as the average of the previous t values. Next as the next value as the weighted average of the past p values. Okay. So because we know that this distribution is proportional to the exponent of xi minus 1 by 2c squared xi minus summation is Tito summation squared. So now you could say that, okay, even this model will be always applicable. So if you have feature vectors x, which is in d-dimensional space, you can just pass it through a FW network, which will give me a single number xi belonging to R. Right, so this is also possible. So it's always how you design these models. You can always have the complexity and the usefulness of the models change accordingly. Now, how would you sample? Sampling is again very simple. X0 from dummy or X0 from P of X0 distribution. So which could have say K values, and then X1 would be P of X1 given X0. And P of Xi would be sampled from P theta of Xi given I less than none. Great. Okay, so this was one of the methods we could do it. This is called the ARMA model. The next is based on choice of alphas, so or other neural networks or the other neural networks or the output distribution, we could have what is called belief networks. So we say that, we are encoding a binary stream. So every xt is either 0 or 1. So what we can do is probability of xi, we could say, is less than equal to I, could be Bernoulli distributed as some function of f theta of x of I. Right. So this is how we do what is called belief networks. So say it will take in all the values x0, x1, x2, dot, 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 xp, or I minus 1, and it will say xi. And I'll put a sigmoid function as well. Sigmoid of f theta of x less than I. Right, so this will give me a number between 0 and 1. If sigma of f theta of x less than I greater than 0.5, we could say this is 1, else it could be 0. Okay. Depending on the choice of f and the distribution, one can have different type of networks. So we have fully visible sigmoidal belief networks here. As I was telling, you could have P length. Again, you could have any P length. And this is exactly what I'm doing. So instead of having this, I could have a shallow neural network where we will take all the values. So x0 to y minus 1, one layer neural network, which will give me hi. And then I will have one more layer of neural network, which will give me an MLP, which will give me alpha hi plus bi, alpha transpose hi times bi, whatever you want to. This is say one layer neural network. Right, and then you can make the model learn on a binary cross entropy loss and so on. So here the loss would be the weights of theta star would be r the mean over theta minus of xi log of sigmoid of if w of less than xi minus 1 minus xi log of 1 minus sigma of f w of xi. Right, so this is just going to predict if the current token is going to be 0 or 1. Because this is my binary cross entropy loss because of the Bernoulli assumption. I've shown this multiple times before. Okay, so the recurrent neural networks, as you will see in the next class, and you may have already known, can also be used for predicting the next token. What it can do is say, I will use xt minus 1 and a hidden state. This is called a memory. ht minus 1 is a memory term. And what I'll do is ht will be defined as some combination of the previous memory and the current data. I'll tell this to be xt minus ht, and my xt will be g of u of ht minus 1. Rather capital just h of ht. So what this is going to do is, this is going to take the past, keep past memory, and update based on current experience. This is also, see, LSTMs and RNNs need not always be. So now sequence to sequence models, what we'll do next day, you did not always use x1 to t minus 1 to predict xt. So these are all architectures. You can also do something like x1 to t and predict y, like in machine translation. Right, so where you're predicting a different variable altogether. For example, if you're going to have epilepsy or not based on 1 to t and predicting the value of y. Right? So we'll see why RNNs suffer from vanishing gradients next time. And this is exactly the same model. So what this will be like, ht is going to be u of ht minus 1 plus m of xt, and yt is going to be a sum of the activation function of ht. And this is going to continue. This is generally a tan h function. So you can see that ht, this function, at the end of the day is again based on u of ht minus 2 plus m of xt minus 1 plus m of xt. So this is by induction, you're going to get all, so this is actually going to get u square ht minus 2 plus um xt minus 1 plus m of xt. So if you go again another step, you're going to get cube ht plus u squared m xt minus 2 plus u cube. Am I doing it correctly? Sorry, u m um xt minus 1 and mxt. So you can see that this all depends on, so this will all end up depending on xt minus 1 and all the way to x0. So xt depends on x0 to t minus 1 if trained in an autoregressive manner. So you could train it in a sequence to sequence manner, then it will depend on, then yt will depend on, in sequence to sequence, sig yt depends, or yt depends on x0 to t. Okay, so with that we come to end of what are the concepts of autoregressive model. The next day what I'll do is I'll teach you sequence to sequence models. So autoregressive models are very simple. It's like predicting and getting a neural network, taking peak channels and predicting the next output. That's all autoregressive models are. It's like taking a window of P length and just predicting the next, or you can use an RNN, which takes the entire history in the past and predicts. And we'll learn about sequence to sequence models or sequence models in like RNNs, LSTMs, and GRUs, and attention models and transformers in the next class. It will all be like architecture based in the next class, the only architecture based class we'll have. And yeah, with that, we have mostly covered all generative models. I'll just start showing you how we will implement the DC GAN. Okay. The problem that I'll do here is implement DC GAN. So here what I will do is I am taking a 50 length Z being sampled from uniform -1, 1 to the power 50, right? Which is a deconvolutional GAN, right? Deconv GAN. It's a deconvolutional GAN. What I'll do is I'll first project it, this 50-dimensional vector, to some, say, 256-dimensional vector. I'll reshape it into, say, 4 cross 4 cross 16. I don't remember the exact value, but this is one of the methods, right? Then I will use deconvolution, say, and I will use batch normalization. The different layers, and I'll maybe get, and some trimming and some clipping, and say 7 cross 7 cross 32. And then I will do deconv again and keep doing deconv to 14 cross 14 cross 8, say. And then I will again do deconv. I'll get, say, 28 cross 28 cross 3 or 1, depending on whether I want. Yeah, I don't want colored images. So again, I'm doing the MNIST. It's on MNIST. MNIST is 28 cross 28 plus 1 dimensional space. Okay, so this is the thing. And then I'll take this image. This is my generator. I'll take this image and I will use a 3-layer convolutional neural network on when I'll predict real or fake. X also exists. This is the G theta. This is my D theta. I'll use the DC GAN objective where I'll use the Goodfellow GAN objective. And a key point to note is I'll train generator 3 times for every time training the discriminator. As I don't want, as I don't want the model, as the want the generator to be, as I don't want the generator to be too strong quickly. Okay, then discriminator won't learn. Let's see how we have implemented this in reality. I will stop sharing from my tablet. Yeah, I'll start sharing here. Yeah, I hope you can see my screen. Just we've done a lot of things today. Please go back and look what you're doing. Yeah, so this is my architecture in case I need it. Yeah. It's much simpler code compared to diffusion models and VAEs, but it's a very difficult thing to train models with. So let's see how we have implemented it. See, so first of all, I will load the MNIST data as I've been doing in the past. And then I have these parameters. Say the input is say this, I took a 50 dimensional input and I got I just say converted it to 52. As I was saying 256, I converted it into 5 cross 5 cross 5 cross 5 cross 10, which is 250 dimensional vector. So I'll convert this. I'll show you what I'm doing this generator. See, the generator takes a dense layer and it converts it into 50 dimensional input to it is using an MLP to a 250 dimensional input. And you can see, and then what I do batch normalization and I do reshape into, I do reshape 5 cross 5 cross 10. And then I do deconvolution. I do a couple of layers of deconvolution. So a deconvolution and I take an activation of LU and I say 32 layers. And then for valid and same are a bit different in each case. So the valid and the same says the following. So if you have a valid padding, this is not going to pad. Same is always going to keep the dimensions to be same if required, and that is the same padding. Here you will see wherever you have 2 by 2 as the input, it means that it will double. The strides being 2 by 2 in our deconvolution means you're upsampling 2 times and then taking convolutions. That's what this con Fourier transpose does. You upsample twice and then take a convolution. Okay. So then we have another con Fourier transpose. So I have one here, one here. So what will happen is when I do this valid, this will convert into 7 cross 7. 5 cross 5 will be going to 7 cross 7 because there's no padding and it will only 7 cross 7 data can come to 5 cross 5. It's again strides of 1. So 7 cross 7. So you can think of deconvolution as the inverse of convolution. So if you had a 7 cross 7 block and you did not do padding, it will come down to 5 cross 5 when you do convolution. Okay, and then this will be when you have a 2 cross 2 upsample, so this will become 14 cross 14. And this will become 28 cross 28. And I have 2 more convolutional blocks so that I have enough weights to train the model. In the discriminator, I have conv2d max pool, conv2d max pool, conv2d max pool. And I flatten and predict using a sigmoid function what is the output. So this is the normal classification model. 3-layer convolutional neural network, 3-layer CNN to predict between real and fake data. So now let us see. So we have made the model. We take the input as a noise input and then pass it to the generator. We get the generator function. Then in the discriminator, we take the input as the dimension of the data and pass it through the discriminator, and we get the discriminator model. And we have two different optimizers for the generator and the discriminator. Generation is very simple. You just pass sample from normal 0, 1 and pass it through the generator. And you can see the accuracies. Here, the real accuracy is everything. If you predict more than 0.5, the fake accuracy has to be predicted in less than 0.5. So the back propagation goes as follows. So here you can see for the generator loss is equal to minus log t of x, where x is from generated data. This is exactly what I'm doing. I'm generating the data, generate data of the number of data points I want, and I get the generator loss. And now I do multiple cycles of generator loss, followed by one cycle of discriminator loss, where I generate one set. And for this real data set, I'm going to do, you can see this loss is nothing but log of dx, x from real, and this is not the improvised log, this is the log of 1 minus dx, x from big. And that's what I'm doing. I'm going to make it negative because I want to make a maximum, minimize the loss. I want to update the gradients. Okay, so let's see. This is the model. 50 to 57, 14, 28 is the generator, 28, 14, 7, 3, 22, 88, 1 is a discriminator. I've trained the GAN. If you see as it model trains, it goes towards log 2. See, this is 0.69 would be log 2, and it's like very close to that. And I told that the optimal discriminator value of the entire loss, which is log of d star plus 1 minus log of d star, would be near 2 log 2, which you have shown many times. And it is clearly near 0.4. So you can 1.4, 1.36. The model is really doing well. So if you see, this is my discriminator loss going towards 2 log 2, and this is coming to half of that as log 2. And you can see the accuracies are around 0.5, 0.6, which is showing that the model is performing really well. And now I can load the model, which I'll show. Training will take an hour. And I've generated 90 samples, and you can see these are some of the examples of the generated data. 7, 9, 0. You can see that there are some shapes which come multiple times, so it could be due to mode collapse. And we're not seeing all shapes. Maybe 3 is a bit less over here and so on. And 8s are a lot. Things like that we are seeing. 2s are there, and then something like that. 2s are not there. So this is the implementation of DC GAN. I'll upload the code, and please feel free to run the code and change things here and there and see how you can train. What happens, a special thing to do here would be to convert this objective to a JS GAN and see if it is working. It is working, or we encounter vanishing gradients, and weak generator. Okay. So we'll stop there today, and then we'll begin with models that are going to be, we'll begin with sequence to sequence models, and we'll learn about transformers and state-of-the-art models in the next class. Thank you. Stop sharing. Please feel free to ask your questions in the comments, and I'll answer them.